Welcome to the video lecture on theory of computation. So today in this session we are going to discuss about unit 1, which is nothing but some introductions about theory of computations, like introduction to formal proof, additional forms of proof, etc. So before going inside this, we need to have some introduction. So what is called as computation? Computation is always finding solution to a problem. So, coming on to the history, Alan Turing devised two types of problems called tractable and intractable problems. This is also called P-type and N-type problems, NP-type problems. So, tractable problems are nothing but problems that can be solved in polynomial time, and intractable problems are problems that cannot be solved. That cannot be solved in the sense it cannot be solved in polynomial time. And in 1940, automata is designed like non-deterministic finite state automata and deterministic finite state automata based on the human brain. And 1950, Chomsky devised grammar, context-free grammars or grammars which is used to define structure of programming languages. And the research extended in 1969 by using Turing study. So Cook extended Turing study, so Turing machine. So problems can be devised into NP hard and intractable problems also. NP hard is what computers can easily do, and intractable is what computers take longer time to do. That is called as intractable problems. So this is about the computation introduction, and next coming on to the topic called applications of automata, where it is used. So it is used in digital logic circuits, compiler construction, and then modeling the programs like communication in networks, on-off, operating on-off switches, etc. And then we also have some knowledge about transition diagram and transition table. How to draw transition diagram? So states are represented by using circles, and you can give any name inside these states as state names like Q0, Q1, Q2. Initial state is represented by arrow, and final state is represented by double circle. And the input transition from one state to another state is given by the arrow, and labeling of input names is also done. So from Q0 the input 0 goes to Q1, from Q1 the input 1 goes to Q2. So this is called as transition diagram, and this can be converted to transition table. This column represents states like Q0, Q1, Q2, and we have input transition like 0 and 1. From Q0 the input 0 goes to Q0 and Q1. From Q0 the input 0 goes to Q0 and also to Q1. From Q0 the input 1 goes to Q0. From Q0 the input 1 goes to Q0 itself. From Q1 the input 1 goes to Q2. So there is no zero transition, so it is indicated as hyphen. So this is the representation of transition diagrams and transition tables. And next we have introduction to formal proofs. So we have many proofs like universal truth. Universal truth is it must be true for all possible values or conditions, and we can prove this universal truth by deductive proof, inductive proof, proof by contradiction, proof by counterexample, etc. So we can discuss one by one. So what is called as deductive proof? Deductive proof is the statements of the form like if H then C. If hypothesis is true, then the conclusion will be true. And statement like if A, if and only if B. So if this can be otherwise stated as A is equivalent to B, A if and only if B, or if B then A, or if A then B. Anything is possible. This is called as deductive proof. Next is inductive proof. So inductive proof is done by mathematical induction, where we will have some two steps. In the basis step we will put n equal to 0 to prove any conditions. Then we will extend it to n equal to 1, and then in the induction step we will put n equal to n plus 1 and then prove the formulas. This is called as inductive proof. And we also have proof by contradiction. Contradiction is negation, opposite form. So if H then C, this can be proved by if H initially we will take not C, and then finally we will state it as false and prove that it is if H then C. This is called as proof by contradiction. Next is proof by counter example. Proof by counter example in the sense theorem must be true for all possible values or conditions. This is called as then only it is proved as theorem. If it fails even for one case, then the theorem has to be re-established like some modified by using some modified or redefined statements. For example, all primes are odd is one theorem. So this will not suit for all possible prime values. It is false for prime number 2. So we can state as we can state the modified theorem as all primes are odd except 2. This is called as proof by counter example. And in this session we have discussed some of the basic concepts of TOC, and then in the next session we can see the basic concepts on finite automata like languages, strings, alphabets, power of alphabets, length of string, empty string, etc. Thank you.